You guys know who these people are? You know who it is? Do you anyone want to guess? One's easier than the other usually. There's Ada Lovelace on the left, and on the right, that's Turing. So Ada Lovelace is sometimes called the first person to come up with algorithms because there was this crazy guy Babbage trying to make a computer out of like steam and stuff, and somehow he got to know Ada Lovelace, and she was very clever and started thinking about various mathematical things you can do computationally. And I'm assuming you all know who Alan Turing is. Um, and at some level, Alan Turing faced a very deep question. The question was, is every kind of yes/no question, I'm paraphrasing a little, is every yes/no question, is it computable? Is there an algorithm for it? And he was able to show no. But the first step is to come up with what is a computer. I mean, it was first posed more logically, like is everything computational? The word computational is a little bit vague. Um, okay, so yeah, so okay, so all right, so welcome to the class. So this is I guess algorithms class. I'm assuming that you guys haven't taken a full algorithms class before, though maybe you guys have been exposed to various degrees, but you have all um, signed up for some kind of advanced version, self-selective version. Um, and so we'll figure out what that means, especially as I get to know you guys. But first things first. Well, my name is Kent, and you can just call me Kent. Um, and our class website, so to speak, is just one massive PDF at fundamentalalgorithms.com. It's similar to the ones I've used in the past, and I've just updated some things, and that'll be our starting point. And the goal is to just make sure everything is in the PDF so that we're all on the same page, and so on and so forth. In particular, if things are missing, you let me know. I can update the PDF. The whole class is synced back up. Okay, so what are the most important things? Okay, so we have three very enthusiastic TAs, Peter, Ryan, and Cyril. We haven't quite figured out when to do office hours yet. Actually, in general, I'm usually a little more organized, but I was traveling this past week and I got back last night. So we met over Zoom once, but usually we meet a little more. We'll settle that in the next day or two. Um, I'll go over some of the basic stuff, but in the back of the PDF is the syllabus. It's kind of boring, but you should check it, read it, and clarify anything ahead of time. And I'll take questions next time, but I'll do some stuff in a moment. So the all the homeworks will be listed there. There'll be a class schedule listed there that's quite detailed. So initially I've just dropped in, the class schedule from past classes. Like I taught, I guess, an quote unquote graduate class last semester, but it's actually very similar material to the undergraduate class, maybe a bit faster or something, or a slightly different selection of problems. And that's going to also be my default to at least get us started here. And then as things go along and I get a better sense, we might, if we go faster, we'll have room to do things, or if, uh, well, we can discuss ideas in a moment, but just the default is some kind of standard algorithms class. I kind of have a reputation for a slightly harder version of the algorithms class, so maybe it's already well suited. But depending on what you guys take to, we can do more creative things, etc. So I'm open to this, but I mean, I'm very open to this. But in the past, I've sometimes been a little too progressive in my teaching, and so I thought I should start safe. Okay. All right. So okay. So here are maybe some of the most important parts of the syllabus that usually people care about. Okay, so yeah, so we have these three TAs. We have almost as many TAs as students, so that's already fantastic. Right now we're set up for two midterms and a final, and there's homework on like a weekly basis. And the goal is to just get you through a lot of practice problems. That's what we're really doing in this class. But we have a lot of leniency policies. For example, we'll just drop the lowest 20% of your homework scores. That's like on a problem by problem basis. So each week will be like two or three problems, maybe with multiple parts. But at the end, I'll just list them and I'll drop the last bottom 20% of your homework problem scores, whatever 20% rounded up to the nearest integer. Uh, we also have an unusual late homework policy. So two things. As soon as you submit your homework, like the next day I'll put out solutions right away. But you also notice that there's a late deadline that's like 3 days later or something. Actually, I think we have to finalize that. But that actually means that you can look at the solutions, and if you want to change your solutions based on what you've seen, you can, and you just automatically get marked off like 65, I mean 35%. You know, there's a max of 60 or 65. I have to check what our number is. Okay, but so this is partly so that like sometimes you'll bomb a question, but you don't have to feel so bad, and then partly it's also to incentivize you to look at the solution and think about what you submitted, things like this. So, so that's maybe a unique characteristic of this class. And then, yeah, as alluded to, I'm just starting as a default what I've always done in the past. But based on how things go, we might innovate, and maybe I'll talk to you guys individually, like, how does this sound like a good idea, or would this sound fun, or things like this. But potential things that we can always try exploring is like if you guys wanted to flip the classroom where you do the reading ahead of time. I've recorded lectures from past classes, for example, and we could spend the time just doing problems together instead. Maybe that's more fun, on certain topic basis. Another topic might be a little more complicated to explain, in which case we'll just stick to a regular lecture. That would be an idea. Depending on our pace, we might have extra time at the end of class. The default is I just find fun topics, interesting topics. I'll try to find something entertaining but stimulating, something that sort of alludes to research. But, if alternatively, we can do something like I can find a list of, kind of like edgy research papers, but somewhat more accessible than average or something. And we can divide up into groups, read the papers and present them to each other, things like this. Another crazy idea I was brainstorming with TAs, we could even try doing something where like I even come up with a research problem. We spend some time doing background. We could just spend a day trying to pretending we do this as a full-time living or something. But so there's all these possibilities, especially towards the end of the class once we finish covering stuff, or in the intermediate. But yeah, it's a small enough class that I can kind of probably get a very good feel for how we're all doing and adjust as we go along. So right now I have this like kind of a ton of material for the standard thing. That's our default, and depending on your enthusiasm, we can do different things. Okay, there's plenty of tricky problems you'll find in the book, so hopefully one way or another you'll be challenged. Okay, and presumably you want to be kind of challenged, or else you would have taken the. Okay, good. I think that's it for the boring part. Any questions? Yeah. On a problem by problem basis. Yeah. So the late deadline will be problem by problem basis, and the grade scope will have different entries for each problem so that it separates out the submission times. Oh, and there'll also be some multiple choice. Oh, yeah, that's a great question. Oh, this is in the syllabus, but we're going to let you work in groups of three. At least that's what I've done in the past. It was more useful. It was a big class, and then I was too lazy to update it. But if so that's okay. Um, uh, but obviously, the homework is largely for your benefit. If you don't try to do the homework, you're just going to get railed on the exam. Um, so, but at least work together. Maybe it'll also divide up the typing. There's also some typesetting rules. So we're going to have you learn LaTeX if you don't know it already. But there's some pointers to it. You could probably sneak in Markdown and compile it to LaTeX. We wouldn't really be able to notice. Um, yeah, yeah. So groups of three, I guess is the default. Yeah. Other questions? Obviously, it'll make more sense once you've had a chance to look at the syllabus. And I assume nobody wants to watch me read the syllabus out loud, and so you can just read on your own, and we'll do more questions next class. Okay. Okay, good. I mean, I think maybe the first thing is I will probably finalize it tomorrow, but our first homework will be due next week. And then we're thinking of having homeworks due on Thursday as opposed to Wednesday, because the TAs thought having an office hour like right after this class or something would be something you guys would like, guys and girls. Yeah. So we'll do weekly kind of Thursday homeworks. We'll skip when there's an exam, things like this. And you can always skip 20% of the homeworks. Okay. Other questions? All right, let's let the fun begin then. All right, so introductory lecture, you might know a lot of stuff I'm talking about. You can tell me after class. Okay. So I first I'm going to try to convince you that you already know a lot about theoretical computer science. Okay. So let's start with something you always do, right? Just counting, right? One, two, three. So how high can you count with your fingers? Don't be shy. 10, right? So one, two, three, four, five, seven, and 10. Maybe start from zero. All right. Can anyone do better? Yeah. And 10. Yeah, I can like 11 or something. Oh, okay. So 11, 12, 13, 14, 15. Oh, okay. You might get a better number. Yeah, yeah. You don't, yeah. Okay, 1023 if you do binary, right? You know, all these combinations and stuff, right? So, so that's already quite the leap to go from 10 to 1023. And in fact, you guys have been noticing that maybe you could turn these into like ternary digits or something. But then you lose a thumb. So, okay. But okay, so this is the point, right? Like, how many tallies is that? Yeah, I mean, like nobody knows because it's an insane system. I think it's 23, but no one has ever verified this. Okay. And this is the basic point, right? You already know this. You know that the right hand side is much more efficient than the left hand side. Left hand side is called unary notation. It's just one pebble per thing. And then in the right hand side, of course, you only need two digits. So, you know, what's the simple point? So in decimal notation, where each digit has one of 10, with k digits, how many numbers can you express? 10 to the, what the hell? How is that possible? It was at 70%. Okay, one sec. Does anyone have a charger? Okay, all right. Weird things happen on day one. USB-C, yeah. Okay, perfect. Might be time for an update. Thank you very much. Okay, so there's 10 to the k numbers you can express as k digits. You already, of course, knew this. This is not new, but it signifies something important. It's a combinatorial explosion, right? Every digit lets you express 10 times as much as before, and there's a huge number of combinations. Numbers are relatively simple, but this is going to happen in all the problems that give us a hard time. Okay. All right. So that's one thing you already knew. All right. Here's another one. Okay. So I'm going to think of a number between 1 and 100. I think you guys have played this game before. I played it in like second grade. It would be like we couldn't go out to recess until we guessed the teacher's number. So I think of a number, and then you're going to make a guess, and I'm going to say, oh, my number is either over or under your guess. Okay. So I've thought of a number, and now you guys just shout out numbers. Okay. 50. Over. Okay. Under. 63. Under. 55. Over. Over. Under. Okay, so you got it in seven guesses. That's not bad. Some years have actually been worse. I think you guys are slightly suboptimal. But anyway, but you guys all played this game and you guys all clearly get it, right? So there's a slow way to guess, right? You could enumerate the things 1 to 100, and you would definitely eventually get the right answer. So it's not an issue of correctness, but as you know, the fast way is to keep trying to find the median, right? And it's a funny thing because the name of the game is guess the number, but you're not guessing at all, right? You're deducing the number. You know that I'm switching a number in my head based on whatever number you guess, right? So you are deducing, and you're always trying to eliminate the number of possibilities. First guess 50, you get rid of half the range. Next guess 25, you get rid of half of it, right? So you're having a number of possibilities from a certain adversarial worst case perspective. Okay, so how many rounds does this take, and how do we calculate, right? How would we mathematically express how many rounds it takes to get from 100 possibilities to one? The log, and in particular, log base 2, okay? So the log base 2 is going to be the number of times you have to half to get from 100 down to 1. It's going to be a fraction because it's going to be a little awkward. You guys know what this roughly is? It's 6 point something. How did you come up with 6 point something? Okay, so yeah, 2 to the 6 gets me under 100 to 64, 2 to the 7, 128. That's over, so there's got to be some number in between. Okay, so now is this 6 or is it 7? So if you divide by 2 6 times, then you'll conclude that there's strictly less than 2 possibilities left. There'll be some weird number, 1 point something. But you know it's an integer, so it'll be 1. So you need 6, unless you need a 7th one to pin it or something. I'm not sure. Okay, but you need roughly 6 rounds. But it doesn't really matter. I'll never care about the difference of 1 round. But okay, good. So you guys get all this. Okay, so those are really two sides of the coin, right? They're inverses to each other. So on the left we have an exponential function, 2 to the n, right? 2 times 2 times 2. This is the thing that grows astronomically, right? And the other we have the log, okay, which is doing the opposite. How many times do I have to half to go from this number down to 1? Or from 1, how many times would I have had to multiply by b to get n? Okay. So, all right. So I was trying to think of a dramatic example to try to really beat you over the head with this. How many atoms are in the universe? Doesn't have to be an exact count, or roughly. A million? Many. 10 to the 100? Okay, that's one guess. So you can get closest. Yeah. 10 to the 120? Higher? Okay. Anyone else? 10 to the 40? Okay. Lower. Oh, you want to play over under? Okay, so it's over 10 to the 40 and under 100. Over, roughly. Uh, right. There's 10 to the 82. I guess I don't know how they estimate this, but they estimate there's 10 to the 82 atoms in the universe. It has a name. What's the name of this again? Named after the this English guy who also verified Einstein's relativity theory. Huh? He also came up with the H10. Yeah. Yeah. It's the Eddington number. So Eddington's like some super interesting guy. I think he's also like really into biking or something. Like Eddington is like an article unto itself. Um, but yeah, I think he was the guy who set up the experiment where so Einstein predicted that there's going to be an eclipse like 1 second off or half a second off from what Newton would have predicted because light has to bend according to Einstein. And Eddington somehow, I think, was the guy who did this. If I made that up, then okay, it's on YouTube forever. Okay, um, so 10 to the 82 atoms in the universe. So let's take the log and see what happens, right? So if I want to take log base 2 of 10 to the 82, what comes next? Yeah. Okay, we can pull this out, right? That's how math works. Yep. Oh, that's true. But do you know what log base 2 of 10 is? Yeah, that's true. So then you should be able to figure out, then it would have to be half, I guess, of, if you know log base 2 of 100, then you should be able to figure out log base 2 of 10 for the same reason. Something like this. Yep, so that's a good observation, actually. I hadn't thought of that. I'm being slightly resistant because I prepared ahead of time. Uh, So you have 3.32, which you also could have gone from halving log base 2 of 100. And I guess you multiply these things together, you get something like 272. So the log will get you from a number of atoms in the universe to a number you can technically count, with your fingers, right? Okay. So now what happens if I take the log again, the log base 2 of number of atoms in the universe? Well, roughly up to an integer. Huh? 15 or 18? Should be a little bit more than 8 because 2 to the 8 is 256. Okay, something like this. Okay, I didn't work it out. Um, just because of this. Okay. So you take the log base 2 twice, and you go from number of atoms in the universe to just 8. Right? So log is supposed to be compelling. Good example. Okay, so if you just came in, you haven't missed anything profound yet. Um, but the point I want to make is that at some level, in theoretical computer science, we're trying to take much more sophisticated problems, but distinguish between situations of combinatorial explosion, right? Where just so many possibilities out of control, no matter how strong your computer is, you can't search it all. Or situations like binary search, where there may be a lot of items, but there's enough structure that you can find what you're looking for very efficiently. Right? You can do binary search over the atoms in a universe. It'll take 270 iterations. That's nothing for your computer, right? But that's because we're looking at a total ordered set of numbers, and there's an extremely strong structure, right? But what you want to do is you want to walk into a problem in the wild, and you want to say, oh, can I do something like binary search? Can I take something very complicated, it's very complex, and actually find the thing I'm looking for, solve the problem? Or is this problem something that's actually arbitrary, complicated? There's no order. You have a combinatorial explosion. Yeah, and at some level, it's distinguishing these two regimes. And I would say we don't fully understand this difference. Okay, so algorithm is really kind of about structure of problems, structures of things. Okay, all right, so good. All right, so now let's get into some more conventional topics. So it wouldn't be an algorithms class if we didn't start with sorting. I guess you've all probably been exposed a little bit to sorting before. Um, at some level, the first lecture is always a little bit conservative to make sure we just kind of stay on the same page. If it's way too conservative, tell me afterwards and I'll make some adjustments. Okay, so, okay, well, I'm going to force you all to participate. So here's n numbers, I guess between 1 and 11, and the goal is to put them in sorted increasing order. Yeah. All right, so let's sort these numbers together. What would come first? Okay, 1, 2, 4, 5, 6. Okay. Okay. Thanks for playing along. Okay. So this listed the numbers in increasing order, or weekly increasing or whatever. But at some level, your input is some chaotic thing, and you want to list the numbers, right, to be increasing. Right. Once it's sorted, then you could do things like binary search. So obviously, this is very useful. Okay. So how does a human sort? How did you sort? What was the first thing you did? And yeah, you asked yourself what comes first, probably, right? I think this is what most people do. And you went through the list and you said, okay, I think it's 1. And so we wrote down 1, right? And then what did you do next? Yeah, you asked yourself what comes second, right? And then you went through the list, said, oh, that's 2, and so on and so forth. In fact, this is slightly more convenient because we're also kind of checking off the numbers, so that you can kind of bypass them the next time you pass through. Okay, so that let's call it human sort. There's a real name for it. I always forget, right? But this is what I think a lot of people would do. And let's try to estimate how long this algorithm would take. right? So at least the way I imagine it, there's an outer loop, right, where each outer loop generates one more number. There's an inner loop, right? So what's sort of the bottleneck if I'm thinking about our human sort? How should I break down the running time, right? So there's this outer loop, and then for each number, the hardest part is scanning through the whole thing, right? So okay, so how many iterations that's referring to outer loops are there? For n, and then how many items do we scan in each iteration? N, right? We multiply these things together and we get some estimate of n squared. Okay, so the algorithm is going to take roughly n squared time. Okay, so okay, so now we just want to formalize. How do I really state the running time of an algorithm? Okay, and this is where this so-called big O notation comes in. You guys been exposed to big O before in discrete math? So we're just reviewing then. So when we say big O of n squared, I really mean when the input's large enough, it's going to take about n squared steps in the worst case, in the sense that, oh, there's some constant where it takes at most that constant times n squared. Okay? But you still might look at this, and you might say, okay, that looks all mathematical, but well, like, what the hell is a step? Right? What do we mean when we mean steps? And of course, that's going to vary depending on the language you use, computer you're using, the compiler, all this nonsense that has very little to do with the problem. Okay? And the point I want to make is not so much what's the definition, make sure you know the definition. It's that when the big O notation hides that constant for you, right, and you're focusing on the n squared, which is really the kind of the characteristic of your algorithm and is the characteristic of the problem, right? Okay, you're not worried about what computer you're working on. You're not worried about the programming language. And you can start making a real independent theory of algorithms, like a real theory that you can take from one computer to the next, one problem to the next, one language to the next. Okay, so that's what the big O is really there for. Okay, to abstract so you can tell apart the trees from the forest. Okay, good. So, we're making great time. Okay, so the usual question, and I presumably many of you know the answer to this, but any question, we have some preliminary algorithm, we ask ourselves, can we do better? Right? And just to try to heighten the stakes a little bit, n squared is a natural running time in the sense that that's how long it would take to compare each number of your input to each other number in the input, right? So when we're asking if we can do better than n squared, we're really asking, can you do better? Can you somehow sort all the numbers without actually comparing all of them to each other, right? Some of you may know the answer, which sort of spoils the suspense, but naively, this is sort of an interesting question. Okay, so right, do we really need all the comparisons? Okay, so as a warm up, then let's take a slightly different perspective. Again, I feel like I'm working towards something many of you know, but it's sort of like the approach is something that we can take to more complicated problems later. Okay, so this is the question of verification. So any problem you want to solve, usually an easier question is how long would it be able to double check a correct answer? Okay. Yeah. So given an array that's supposedly sorted, how long would it take to verify that it's sorted? Okay, so I heard n, but why or how? Okay, so what would you do? Yeah, right. So you can compare these one by one. And if they are all increasing, then I guess I mean, and then obviously it's in sorted order. The fancy word is that, the transitive property, uh, guarantees it's going to be okay. A less than B, B less than C, A is less than C. Okay. So, you can verify this thing in linear time, right? Okay. So now our question is okay, we know we can sort in n squared time, and we know you can verify a sort in n, and of course verifying should be, I mean, faster than sorting, than actually doing the thing, constructing the solution. And the question is, can we get all the way down to the verifying time? Right? Okay. So All right, continuing on then. Um, I'm going to unveil an algorithm you guys probably all know, but I'll try to do it like a teacher. So here's maybe a warm-up situation. Slightly easier problem. Suppose I gave you two sorted lists of roughly equal size, and you want to combine it to get one sorted list. Okay, how long would that take? Okay, how would you do it? So if I had like these two lists, what would come first? It would be one, but why? Yeah, so go on. Nice. Okay, so I think what you have in mind is I'll first compare the beginning of the two lists, right? Because whatever's the smallest number, it should be the smallest in one of the two lists. You say, okay, well that would be one, right? And then what would you do? You'd move on to the next number in your list, right? So whatever's the second one should be either the top of the remaining list or the beginning of the other. And you don't have to check everything else because things are sorted, right? So this is sort of a very common sense thing to do. And you'll end up looking at each number, the pointers will work through. So you'll spend linear time, n time if there's n total numbers. Okay, so this is sometimes called merging two lists. For some reason, I wrote out the pseudocode, even though I think we all agree on what's supposed to be, right? People always make a slight bug at the end because sometimes one list will end before the other. You have to remember to collect the other things, but if you take your time, you'll always get this correct. Okay, so it's not worth looking at the code. It's just going to make it seem more complicated than it is. All right, that's all we really need then for our algorithm. Okay, we're going to do a recursive divide and conquer algorithm, right? I'm going to take a list. I'm going to split it arbitrarily in half. I'm going to sort the first half, sort the second half, and then I have two sorted lists, and we'll use what we just described, this merging routine to get one combined list. Okay? But the question is, how do I sort the first half and the second half? It seems a bit like cheating. So what's the magic word? Recursive. Okay? So we are going to use recursion to sort the first half and the second half. But otherwise, it's very appealing, right? This is like only 3 lines and you're done. Okay. Okay. So how do you design a recursive algorithm? Because, well, probably this algorithm you all know really well, so you're very comfortable with. But in general, recursion is a little bit spooky, right? This idea that I can just call itself to solve itself and things like this. Okay. So the first thing and the most really the only thing you have to do at some level is figure out what your algorithm is trying to do. Okay, this is called the recursive spec. You'll always have to do this on your homework, no matter what LeetCode says. Okay, did I get that right? It's called LeetCode? Okay, all right. Okay, so in a recursive spec, I basically just want to define the function that I want to implement. And what that's going to, and I want to be very formal and precise. And what that's going to do is that's going to set up a contract for what happens on the recursive subcalls. Okay. So by defining what we're going to implement, it also guarantees what I can rely on when I use it as a subroutine. Even before implementing, I know it's going to give me this, right? And without really formally establishing this, you can't actually prove its correctness. So we're going to do that first. So the first thing is we need to give it a name and define some parameters. So I will call it sort, and then it'll maybe take some array of numbers. Sometimes I just write 1 to n to make it really clear that I'm going to use 1 indexing instead of 0 because I'm a teacher and I can decide my indexing. Okay. So the numbers, index 1 to n, right? So in some kind of list. And then I'll put a colon here. And we're not going to implement the function. We're just going to define what it's supposed to do. Okay. So who wants to suggest one of these sentences? Okay, so let's do like a little bit more slowly. So just to establish like input and output. So I might write something like given, n numbers, a 1 to n, right? And then always a good word here is returns, or you could say outputs, right? It returns, and now what? Yeah, maybe, list maybe b1 to n of the numbers in sorted order, or something like this, right? It's always going to feel a little bit clumsy and a little bit boring. Okay, so that's roughly what I wrote here. Okay. So I guess we could have been a little more precise. This was partly my fault. We could have said an array of comparable elements. Our algorithm worked for any system where things are comparable. So it could have been like names, and we're doing alphabetical order or something like this. Okay. Good. So again, the really important points. We want to make sure we declare the input and the output. And I say this partly from the perspective of grading your homeworks, where when you don't do this, it's like no one knows what's going on. Okay. But what it really specifies is a contract the algorithm must fulfill. And then now when we start doing recursion, right? Now when I say, oh, I'm going to call this function to sort the first half and the second half, while we're still implementing it, so it feels a little bit funky, but I know there's this contract I'm going to fulfill. Okay, and that makes it reliable. And then when it comes to proving that this algorithm is correct, your recursive spec should be exactly your induction hypothesis. So next class we'll do kind of a slower class on induction and do some stuff you might have covered in discrete math. But at some level, you can't really ever prove correctness without doing what we just did in some form. Okay. So you might as well do it before you start trying to write your algorithm. Otherwise, you just have to do it at the end. Okay. It might seem, a lot of what we're doing today might seem a little silly for a relatively simple problem, but I'm trying to establish, kind of good fundamentals for when things pick up. Okay, so now that you specified a recursion, it's not very hard to expand out our 3-line code into some more formal looking pseudocode, right? So maybe the only thing to be really careful about is the dreaded base case, right? But this would be the easiest thing. If the array has 1 or 0 numbers in it, there's nothing to sort, you just return it, right? But you just have to remember to include that in your code, okay? And then otherwise we'll do exactly what we said we would do. We found this number m, which is splitting n in half. I'm splitting the list in the first half and the second half. And then we're just calling merge sort. I guess we're calling it merge sort now. But this is the function that I am defining, and I'm using it to implement itself. Okay, but it's not that big a deal. Yeah, if you describe it in this kind of recursive way, you can get yourself tied up into knots. But it's not a big deal. You've already written the recursive spec. You've established a proof by induction, and you're just kind of executing it on a computer. Okay. All right, so that's the algorithm. Not a big deal. So I won't do it. I guess I won't do it today. But if we wanted to do a very slow, only out of trying to keep things fun, if we wanted to write a very careful proof by induction, all you really need to do is show that your algorithm actually implements your recursive spec for any size n, right? So as I think you guys know, what you want to do is you start with a base case, small numbers. Oh, it works for an input of size 0 or 1. And then by induction, if it works for n, or you want to show if it works, for some arbitrary input size n. To that end, you need to show that you can assume that it works for anything smaller than n. And yeah, but we'll do this more slowly next class. Okay, we're going a little quick, so we'll see. Okay, so the next step then in our kind of introductory algorithm analysis is try to figure out the running time. And for some reason, I thought it would be interesting if I tried to give some pictorial representation of what the algorithm is kind of doing, right? It keeps breaking things half, half, half. And you have sort of this massive looking thing. So the top part in black represents the parts where we're breaking the input in half, and the bottom parts in red is when we're merging things back together. So I think every red array represents a sorted array. It's going to merge back together. Okay. But it's a bit of a messy, messy thing. So how can we account then for running time of this beast? Okay. So, okay. How does one uh, uh, do a running time analysis? Okay. So okay, let me think a little bit. Right. So what do we even mean by running time analysis? Okay, we're gonna, for one thing, start throwing some math on this. What I want to do is to be able to quantify the worst case running time, and we're gonna at some level mathematically model the running time. So the first thing you need to do is you need to set up some variables. We're gonna try to define some function t of n. I chose t because it stands for time. And then what should I write on the right side? Well, okay, actually, one step before that is I just want to write down what it's supposed to represent, right? This represents the worst case time for an input of size n. Let's give it some meaning, which I think you implicitly understood. But let's give it some meaning, okay? And now then let's start trying to upper bound this thing, right? So like you said, the first thing we can do is start with some base cases. So like 0 or 1, that's pretty easy. And how long would this take? Yeah, some constant. So you can just write 1. Okay, so implicitly we understand that's represents some unit of something, whatever. Okay. Now, in the more interesting case, right? I want to be able to model an arbitrary n, right? So how would I first even model this? We can specify a recurrence. So the algorithm is recursive, right? It calls itself. So t of n may be a function of t of smaller numbers because it's calling itself, right? So what would be a recurrence for this? Yeah, so if we wanted to be really careful, because there could be odd numbers, one would round this up. There wouldn't be a 2 here. Okay, that would be a very relatively precise one. But let's quickly go over. Actually, this is not correct. I wrote the wrong thing. What did I do wrong? Yeah. Okay. Even C is wrong. Yeah. Yeah. So merging actually takes linear time because I go through everything. Um. Okay. Good. Floats. Ah. Yeah. Yeah. So I'm going to get there. So this is not a big deal. This is really going to be. Okay. I'll be a little bit. This is what you guys are hoping for. You don't have to put the big O there as well. Okay? And it's not very hard to justify this formally, and I do it a little bit more slowly in the notes, but it's not worth digressing for 10 minutes. But morally, what's going on is I'm really only interested in the writing time for large n's. Right? The slowest algorithm is going to be instant on an input of size 100 or something on your computer. Um, and once n is a million, what's plus or minus 1? Right? Especially if I'm slashing by half. And if instead I slash by, 49.99999, not a big deal. Okay. Um, but it's not very hard. In fact, here's one trick. So you can define T of n to be max time for any input. So a slight difference in definition of size at most n. Okay. It's essentially the same thing, but slight difference in the definition. So, whatever would have been the max of T of n. Okay. So that means that now it's very clear that when n gets bigger, this number can only go up just by definition, in case there was any issue with the previous definition, right? So t of n is always less than t of n plus 1, and so forth, right? Now, suppose given n, I'm going to let like n0 be equal to like 2 to the, I'll take the log base 2 of n and round up. But what I'm really doing is finding the next power of 2. That's all n0 is supposed to represent, right? And then, of course, t of n is at most t of n0. Okay, because it's just going up to the next power of 2, and by definition, okay. And if it's a power of 2, then this recursion is perfect. You can always divide exactly by half, right? So at some level, I can always imagine the input is a power of 2 by redefining this, and then just work out the power of 2. And once it's revealed at the end, you'll say, oh, it's not a really, who cares if n multiplied by 2? Okay, so that's formally fine. And that's totally not cheating, and we'll cover these cases very easily, right? But you don't have to like give me the same explanation every time this comes up, which will be every time. You can just write 2tn over 2. Okay. All right, so, okay, so good. So that's that. Now, so now we've modeled the running time, right? And you can, the equation makes total sense. It's saying, okay, so solving input of size n is going to take the running time of solving 2 instances of size n over 2, plus this merging, which takes linear time. Okay, and now we want to try to find something that's more closed form. The first step is to model it. The second step is sort of to solve it. Okay, so we're going to use something called recursion tree. Have you guys seen recursion trees before? Oh, have you? Okay. All right, this is okay. Afterwards, you guys can give me feedback on how calibrated this is. But in any case, the first step is to draw some kind of tree that models your computation. Okay, so in our case, the root will represent the original problem. Okay, and I have 2 subcalls, right? And so I've created 2 children. And each of those will have 2 children, 2 children, 2 children, 2 children. So you're going to get this binary tree. And then down at the bottom, you're going to get a bunch of leaves of size 1 or something. Okay. So you just write this and you start to get a feel for what the algorithm, the computation is going to look like. Okay. And then the next step is we're going to annotate each of these nodes with the size of the input. Okay. So like the root, what's the size of the input? N. And then those 2 children, what's the size of those inputs? N over 2. And then at the next level? And so forth, right? Okay, so I've drawn a tree. I have some sense of how big the inputs are. You imagine the next level will be n over 8. You just write a few so you get some feel. Okay. And now what I want to do is I want to look at my algorithm and figure out for each level what's the total running time spent at that level, excluding the recursive subcalls. Right? The tricky part of it is like how am I going to account for the recursion? So we're going to kind of separate these out. Okay? So for example, this problem here, this top problem, how much work do we do excluding the recursive subcalls? N from the merging, right? So I'll need, N work here. And if I go down to the subproblems, like this one here, how much? N over 2, right? And same here, okay? And yeah, sorry if this is the meaning. What would be the next level? N over 4, right? Okay. N over 4, N over 4. Here it's pretty straightforward, of course. I'm only describing this stuff because it'll be useful for more interesting situations. Okay. Now what I'm going to do, and this accounts for all the work, right? I have some n work plus work that's going to be accounted for lower in the tree. And then n over 2 work that will be accounted for lower in the tree, right? So this does account for all the work. And now I just want to add everything up. But the great thing about this tree is I can add them up by level. Okay, so here there's only 1, size n, no big deal. Okay, but the next level, if I add these things up, what do we get? and in the next level, and in general, you're going to get something like 2 to the I times n over 2 to the I, and that'll be n, right? The next level would be 8 times n over 8, 16 times n over 16, all the way down to 1, right? So every level is contributing n work, right? Good. So now we're very close. If I could just count the number of levels, then I'd be done, right? What I really want to do is I want to add everything up. Okay, in this case, all the levels are the same, so we just have to count the levels. How many levels are there? Okay, log base 2 of n levels. Okay, so you're going to get n log n, some constant, right? And that's your n log n running time. Okay, fine. Okay, so much for that. So presumably, had everyone seen merge sort before? Had everyone done this exact recursion tree before? Okay, well, okay, yeah. Uh-huh. Oh, I couldn't care less. Yeah, you could write whatever you want. Equal O and log n is fine. Yeah, I don't even, I think everyone in the world does equals. Yeah, yeah. Okay, this is just a warm up as friends. Okay, yeah. Do we generally assume that log is going to be base 2? There's a good answer for this. Anyone want to suggest an answer? Yeah. So some level, even if this was like some log base C of n, this is, log base 2 of C, if I did it correctly, times log base 2 of n or something. And so when you start doing this O, it's just going to get absorbed. It is true that if that base is a variable, which if you're doing approximation algorithms or like various other things, if there's an n in there, 1 plus 1 over n or something, then you have to be more careful. But if it's a constant, and it's fine. Other questions? Questions make me feel like I'm doing my job. Okay. All right. Well, maybe this will be the first class where I went too slow in 5 years. All right. All right. Has everyone seen lower bounds for sorting before? Are you kidding? Okay, good. Uh, but you've done this proof? Oh, did you? Okay, then okay, we'll go quickly. All right. So we know you can do n log n, but we can also verify n, right? So there's still some gap there, and you might ask, can you do better? Okay. In particular, is this an optimal algorithm, right? That's really a big question. Okay. So the question is, can we prove lower bounds for sorting, right? Sort of a deep question. And in particular, okay, we want to show that it'll take some big omega times some function of n, and big omega is like big O. It's at least some constant times that function. All right, so how would we prove this? Any ideas for how to prove a lower bound? Huh? Same way as big O, but opposite. I don't even know if that constitutes an answer. Okay, so if it's already sorted, it's going to take just n time to verify it or something, right? Okay, so it's going to take at least n. I feel good that the lower bound is n because you have to look at the input. But I want to try to do even stronger. How do I prove a lower bound for sorting? Let me be clear. I'm not trying to prove a lower bound for the algorithm we just did. Like that'll always take n log n because it'll always break things down. That's straightforward. The interesting about lower bound for sorting is I'm saying no matter how clever you are, whatever algorithm, mysterious algorithm out there, not even GPT-5 will be able to do better than such and such, right? So how do you prove a lower bound for an entire problem class? Somehow proving an upper bound for a single algorithm is it's not always easy, but the path is much clearer, right? Somehow you have to do some inside out thinking to get a lower bound for a problem. So how do you set up a lower bound? Or any ideas? It's more fun to think of ideas before I like tell you the answer, unless you're all being polite because you know the answer. Yeah, you can imagine there's some kind of so we always think about maybe this okay, so can we think of some kind of competitive agent um that's giving you a hard time, right? And this sort of gets to the word we always think of like adversarial inputs or something, right? And that's like literally an adversary. And people do this for other problems, especially like there's problems you're trying to optimize f of x, but f is treated as a black box, with some properties, it's convex or something, right? But you don't know anything else. And so there's these resistance oracles, for what it's worth, lower bounds, where, as me, as sort of the devious person, whatever the other person is going to do, I can sort of like change the function inside the box because you don't have that much information about it if you've only asked its value at 4 different points. There's still a lot of options, right? That won't be the case here, but that is a pretty good idea. Any other suggestions? No, you just n comparable elements. They're not even necessarily numbers. I just use numbers because it's easier to. Oh, the input is size. Oh, I'm sorry. The input is size n. There's n elements in the input, and I just assume that you can compare two elements. They could be names. They could be something else. Okay, I think that's going to be kind of close. So let's do this. Okay, so the first thing first we should make really clear because I think this also gets to your question. What is the model? Okay, so we're going to just assume that we're working in some kind of comparison model. You can only compare two elements. Okay. And rather than trying to lower bound the running time of something directly, I'm going to just try to lower bound the number of comparisons needed to conclude something, right? What's the minimum number of comparisons you need to be able to confidently output a sorted list? Huh? Definitely need probably at least n minus one, or we know how to do n minus one to verify a sorted list, but we're trying to find a lower bound for making for sorting a list. Okay, so um, okay, and so this is what we're gonna see. So I think this is the most important step in just trying to, even if you had the idea of trying to prove this thing is kind of awkward, right? So the setup is important. So the first, because we don't know anything about the algorithm, we don't want to presuppose anything about the algorithm. So I'm just going to say all I know about the algorithm is that it makes k comparison queries. Okay, in some order. It makes one comparison query, it makes it adaptively. It makes one comparison query, sees the answer, then it compares another two elements, sees the answer. It could do lots of mischievous things in between, but if I only focus on the comparisons, it's ultimately making k comparisons in order, and that's all I assume. Okay, so what does that tell you, right? If my algorithm only makes, at some level, the algorithm is going to make comparisons, it's going to do some computation, I assume nothing, right? But whatever it outputs will be a function of those comparisons, right? So again, I'm not assuming anything about the algorithm. All I know is that it outputs something as a function of k queries, right? Okay, good. So this still includes all possible algorithms in the comparison model. All right, so now what might be a next step? Okay, so, okay, now each query has how many outcomes? Two, right? Yes or no? Okay. So if each query can only have two outcomes, right? So now I'm saying it's f of k things, but each of those k's takes one of two values. So how many possible things can be output? 2 to the k. Each input can only correspond to one output, and there's 2 to the k outputs or inputs, right? Okay, so there's at most 2 to the k possible outputs. Right? That's not bad. We're making some progress without assuming anything about the algorithm. That's the key part. Okay, so on the other hand, how many possible lists are there? N factorial, right? Oh, okay, I shouldn't have said that. That's okay. Okay. That means that if you want your algorithm to be able to output any, it's going to, yeah, all those things could be outputs, right? So you need k to be big enough so that 2 to the k is at least n factorial just to guarantee you cover the solution space, right? Okay. And we're almost done now. We just have to figure out how big k needs to be. So how do I lower bound k? Yeah.
Sorry, just a quick question. Why do we need 2 to k to be bigger?
Oh, okay. So n factorial possible lists, n factorial possible outputs, right? So maybe the list is in sort order, so you just output 1 to n, but it could be any permutation of n could be the output, right? Referring to the indices of the input once you're put into sort order.
Yeah.
So the algorithm, just if it's a correct algorithm, must be able to output any of those outputs, any of those lists, yeah, it needs to be able to output at least n factorial. And we know that if it makes k comparisons, it can only output 2 to the k different things. So we need the number of things it can output to be at least the number of things it needs to output, be able to output, right? And then we have an inequality. And this is that was the hard part, getting up to this point. Right now, maybe there's some mathematical trickiness, but otherwise, like the rest GPT could do something, right? So, okay, so how do we get this down? I want some k is bigger than something, right? Take the log of each side. Okay, so k is at least log of n factorial. Okay, and what is this? Okay, but why? How did you get that log n? So, okay, if your goal is to say k is at least n log n or something. But be careful because it's going to be greater than or equal to. Yeah, but I'm going to say, let's be more precise. We can do this, yeah?
We can say that, let's take only half the terms, and we know they're all bigger than by 2.
Okay, yeah.
Yes.
So the first n by 2 terms are all at least n by 2, right? N minus 1, n minus 2, n minus 3, all the way down to n by 2. Those are at least n by 2. So we can write this thing is at least log of n by 2 to the m by 2. Yeah? And then you're going to get k is at least log of n over 2 times log of n over 2. So that's omega n log n. Yeah? So yeah, this is a very lazy estimate, right? Just say, oh, there's n over 2, there's at least n over 2. But that's actually a good trick, right? And you want to keep your eye out for these tricks. So what big omega lets you do, it really tells apart the trees from the forest, right? There are sharper approximations for n factorial, which you might have done in your analysis class, right? But it doesn't matter here, right? So if you're not worried about constants, this sort of n over 2 terms, at least n over 2, that's totally fine. It got you the right answer. It's obviously at most n over n, n to the n. There's n terms of n, right? So now you know, okay, it's between n log n and n over 2 log n over 2. So you already know you have the right answer just from doing something lazy, right? Not using Stirling's approximation or anything like that. Okay. Then that is, yeah. Yeah, here's the clean version. Oh. Hmm? Oh, okay, my bad. But this is okay? Okay. So what we've shown then um, is that in the comparison only model, any correct deterministic algorithm has to use at least n log n comparisons. Yeah? Okay. All right, so let me just then make this final point, right? So in general, of course, any lower bound is going to be bounded above by any upper bound by definition of lower and upper bound. Okay. What we've shown just now is we showed we got upper bounds and lower bounds that are within a constant of each other, right? If I take my lower bound and multiply it by a big enough constant, it'll be bigger than the upper bound we came up with, right? And and so that's not, I mean, of course it's great that we have a good upper bound. It's great that we have a good lower bound. But what's even greater is that they actually certify each other to be the right answer. I know I can't make the lower bound much bigger because here's the upper bound. I can't make the upper bound any lower because here's the lower bound, right? So they actually mutually certify each other to be the right answer, right? So we know everything about sorting, at least in the comparison. Okay, so this is okay. So n log n is the right answer, right? And at some level, this is the ideal. If we could reach this kind of upper and lower bound for all our problems, that would be amazing. In general, we'll find out there's a class of problems where we have good upper bounds, and lower bounds are harder unless the upper bounds are already so fast. And then we're going to also run into a class of problems that we don't know how to solve and have sort of a funny kind of conditional lower bound. Okay, but at some level, they're two sides of the same coin.